Hello, welcome back to our next lesson here. Today we will continue with section 7.5. This one is discussing special systems. And in our lesson today, we will be determining the best methods for solving a given linear system. We're going to look at how to classify linear systems as consistent independent, consistent dependent, or inconsistent. And then we're going to also recognize the relationships between the lines, slopes, and the y-intercepts within the types of linear systems. So, as we had been looking at two different sets of equations, and trying to solve your x and your y's, we're going to continue with that. Basically, that's what we're going to be doing today. And we're going to find ways how some of these may be consistent or inconsistent, and whether they're going to be consistent independent or consistent dependent. So first, let's take a look at this as a review here. Solve the system of equations by each method. So how would we solve? We could easily eliminate your x's right here by subtracting the two equations, can't we? And then what would we, if you have x minus x, that gives us 0. And then we would have 3y minus negative y. So what would that give us? That's actually going to be 3 plus 1, right? So then you're going to have 4y, and then 21 minus 1 is 20. So 4y equals 20, then you can divide 20 by 4, and y gives us 5 right here. And then if you plug 5 back in to either of the equations, you solve for x, and x is going to give us 6. All right, now let's take another review problem here. Describe the result of solving each system by elimination. So elimination means we're going to multiply by a common number so that we can eliminate either your x's or your y's, right? What would we, let's say if we multiply by 2 so that we can eliminate 4x, and we'd have 4x minus 4x. Well, if you multiply this second equation by 2, this makes it 4x plus 2x equals 12. But look at what happens. When you have 4x minus 4x is going to equal 0. If I multiplied the y here by 2, and then I have 2y minus 2y, that's also equal to 0. So that actually doesn't have a solution, because both variables are eliminated. And so the result is a false statement. Let's take a look at another example here. Okay, so I've got x plus y equals 3. Here this is 2x plus 2y equals 6. If I multiply to eliminate your x's, you can multiply by 2, right? But then what happens? This becomes 2x plus 2y equals 3 times 2 is 6. That actually becomes the exact same equation. And so again, both variables are eliminated, and the result here, the result is a true statement. Now, we've got several systems of equations. So today we're focusing on 3 different systems of equations. Each of the 3 methods has its advantages and disadvantages. And I forgot to point out to you, during this lesson today, you're going to need to have your textbook out. So go ahead and grab your textbook right now and open up to page 300. And you're going to follow along here in your textbook too. We'll start on page 300. Each of the 3 methods has its advantages and disadvantages, and so if you look at the chart on page 300, you're going to see the list of the 3 methods and the advantages and disadvantages for each of those methods. We've got substitution, elimination, and graphing. And there would be some advantages to either graphing or substitution or elimination. There are also disadvantages, and so basically we'd have to just take a look at the problem and determine what would be the best solution. Therefore, it is best to be familiar with each of these methods so that you can decide which method to use. So try to become very familiar with the chart on page 300 right here so that you can know your 3 methods and what would be the best fit for the equations that you have at that point. Now, let's take a look at some examples here. Okay, now, example number 1, if you take a look in your book, this is also page 300. It says to solve for the system, you have x plus y equals negative 3, and then x minus 3 equals negative 2. So if you solve for the x and the y, you end up with 1 and negative 4. Now, since the second equation is easily solved for x, this would be x minus 3 equals negative 2. Then you would do that first and then use substitution. So I can easily solve for x here, can't I? Okay, I add 3 to move this over to the other side, add 3 here, negative 2 plus 3, x equals 1. And I can easily plug that back into the first equation. X, I'm going to use 1 for x. 1 plus y equals negative 3. Then what's y? Y is negative 3 minus 1. And then so y is negative 4. So our coordinate is 1, negative 4. There we have it. That's our solution. Okay, that is your final answer right there, your x and your y. All right, now, example number 2. If you take a look at that in your textbook, you have your 2 equations, the top of the page there. The elimination method should work well with these 2 equations here, because your x's and your y's, the coefficients are different, aren't they? But we can easily multiply each of those equations by some factor that would make either your x's or your y's to be common factors and have to eliminate them. All right, so we're gonna solve or use the x's. Okay, if you multiply by 2 and then the bottom equation by negative 3, we can easily complete that, and by process of elimination, you'll be able to cancel out and solve for your variable. Okay, now, when I multiply the 2 through this equation, I've got 6x plus 8y equals 6. Then when I multiply the negative 3, distribute that through this equation, then I'm going to get negative 6x plus 21y equals negative 93. And that, I can add that together. 6 minus 6x is going to eliminate your x's, and then you'll have your y's left, and then you can solve for y. So add them together, I end up with 29y equals negative 87. Well, what would y be? Y is negative 3. And then I would take negative 3 and plug it back in to one of my equations there. So we're going to take the top equation, 3x plus 4 times negative 3 equals 3. So 4 times negative 3 is negative 12, correct? So now I have 3x minus 12 equals 3. And then I just solve for x, and x is equal to 5. So then my final solution is 5, negative 3. The next example here now, if you take a look in your book here, this is page 301, and you have the two equations up top there. Since both equations are in slope-intercept form, graphing may be acceptable. So remember, from way back, we had the slope-intercept form, so y equals mx plus b, right? And this is in that format, y equals mx plus b. And we can use the slope-intercept form to try to figure this one out. We'll take one of the lines and we're going to graph that. And then you take the other line, you graph that also. And there you have your two lines. And then where they intercept, right there. And the solution here is negative 4, 1, 2, 3, 4, negative 7. That came from calculating the rise over the run, and also the 5 and the negative 3. Remember, those gave us the x-intercept right here, where it crosses the x-axis. Or if your x is 0, you have negative 3 for your y. If y is 0, we'd have, actually it doesn't even cross the y-axis, not yet at least. Okay, anyway, let's take a look at some definitions here. Okay, we've got systems of equations can be classified according to the number of their solutions. Inconsistent systems have no solutions. No ordered pair makes both equations true. There is no ordered pair where it makes both equations true. Okay, consistent systems have one or more ordered pair solutions. If there is just one solution, then it is called an independent system. So independent 1, okay, remember that. And then consistent systems have one or more ordered pair solutions. If there are infinitely many solutions, it is called a dependent system. That would be infinite many solutions in a dependent system. Now, let's take a look at the graphs of some of these systems here. Inconsistent systems have parallel lines. If you take a look in your textbook on page 303, actually you'll see the chart right there. These notes that are coming up here are basically on page 303, right in the bottom of the chart right here. So I'm going to insert that in here. There is the chart, okay, with the definitions and the graphs, and that's what we're referring to right here. Inconsistent systems have parallel lines. Consistent independent systems have intersecting lines. Consistent dependent systems have coinciding lines. And you'll see that. See those examples in your book. Now, for the next example here, okay, take a look in your book on page 304.